Good afternoon, everyone. I welcome you all to the second part of the workshop, which is the topic is item response theory. And I cordially welcome. Good afternoon, everyone. I welcome you all to the second part of the workshop, which is the topic is item response theory. And I cordially welcome Dr. Shumana Datta, our resource person for today's topic. Welcome, ma'am. Thank you for giving us your precious time and for this workshop, So I'm going to introduce ma'am now. Dr. Shumana Datta is an assistant professor in the Department of Psychology at Government General Degree College, Singapore. Formerly, she worked as assistant professor at the Department of Psychology, Faculty of Arts and Social Sciences, St. Xavier's University, Kolkata, and as assistant professor and head of the Department of Behavioral Science, School of Liberal Arts and Cultural Studies, Adamas University. As also the Assistant Dean, Student Affairs at Adamas University, Kolkata, from 2019 to 2022. Dr. Datta did her post-graduation from the University of Calcutta with a specialization in clinical psychology. She was awarded the prestigious Junior Research Fellowship from Indian Statistical Institute in 2013. Dr. Datta is the Honorary Research Secretary of the Bangladesh Psychometric Society and the Honorary Member of the Research Advisory Board of the Institute of Psychometry. She has several articles and chapters in national and international journals and books. She has also one book and one edited volume to her credit. Her research interest lies in the areas of cognitive psychology, clinical psychology, and psychometry. Welcome, ma'am. Over to you now. Thank you.
Thank you very much, Ruchira. I hope I'm audible.
Yes, ma'am, you're audible.
Yeah, okay. Good afternoon, everyone. It's a pleasure joining here, and my sincere gratitude to Devdulla Dattaroy sir, my supervisor and my mentor for a very long time now, for inviting me. Sir, thank you so much. Thank you for this. So today I'll be speaking on item response theory, which is one of the modern approaches that we use in test constructions and validation practices. So without any further delay, I would like to start with my presentation here. So Richard, if you can please enable the participant screen sharing.
Yes, ma'am.
The participants here are research scholars or professionals?
Professionals, research scholars, both.
Both, okay. Master students are there or?
No, ma'am. Research scholars and faculty.
All research scholars and faculty members. Good. Okay.
Okay. Ma'am, I have made you the host.
Okay. Thank you. All right. I hope it is visible. The slides are visible. Okay. Right. So all right. So today we will be discussing some of these things because the topic is on item response theory. I would like to start with the classical test theory, the limitations, specifically the limitations of classical test theory approach. Since all our research scholars and professionals here, I guess the concepts of item analysis and the basic understanding of test construction is already there. So I'm not going to elaborate on this topic any further. So I'll start with the classical test theory approach because it is an approach which has been in practice for a very, very long time now. Right from the beginning of test construction, which dates back to almost 1905. If you think about the first intelligence test that was constructed back at that time. So it's more than like 120 years almost that the classical test theory approach is in practice. And also it is a very popular one because, students, even undergraduate students, research scholars, faculty members with very limited knowledge of mathematics or statistics can also, actually conduct the item analysis using the classical test theory approach. So that makes it very popular and also very, very acceptable. However, today I'm going to discuss some of the limitations that are there of classical test theory approach, because of which, psychometricians and, scientists, social scientists, specifically statisticians, they thought about an alternative approach. And it was during 1960s that finally the Rush model of measurement was proposed. And after that, it has been in practice now. In the last couple of decades, it has been immensely popular, the item response theory. And today, whatever, whichever test you suggest or whatever you want to develop or validate these days, you need to have this knowledge of item response theory, without which it becomes extremely difficult to publish a paper. It's not acceptable anymore. So that's why, there has been a smooth transition from classical test theory approach to item response theory approach in test construction and validation practices. So I'll start with the classical test theory first. All right, my slides are changing, I hope.
Yes, ma'am.
Yes. Okay, all right. So classical test theory, you see, according to this particular approach, the observed measurement means the score which you get, observed score in any test, that is a combination of the true score and the random error. Now, this true score and random error, there is a little bit of understanding that you have to have in order to understand this concept. What is this true score and this random error that we are referring to? Well, so they are suggesting that in any particular type of test or measurement that we do, the excuse me, the observed score, the measurement, it reflects the number of correct responses, right? Mostly the correct responses. Now, this one suggests that the individual's observed score, this relates to his or her location on the latent variable. Means what? Let us just assume this situation. Suppose you have developed a particular test, consisting of, say, for example, 10 items, and you are administering the same set of items to one individual an infinite number of times. All right. So it can be like, 1 lakh times or 1 crore times, whatever, infinite number of times we are administering the same set of items to the same individual, not different individual, same individual, right? What will happen? We will see that the responses will vary to some extent, right? Maybe the first time it will be 6, total score 6. The next time it will be 8. Then again it can be 9 or 10. So there will be variations, right? This infinite number of times. Now, if we just take an average of these infinite number of times the scores which you are getting, if we make an average of all those scores, then what we get is the true score of the individual, right? So true score is basically the true ability of the individual without any kind of error, without any kind of discrepancies, right? Now the question is it actually possible to administer the same set of items to the same individual an infinite number of times? Well, the answer is no. Why? Because after a while, there will be a practice effect, there will be a fatigue effect. Okay, too many other factors will start intervening and influencing the scores, right? That's why we do not administer the same set of items to one single individual an infinite number of times. Rather, we tend to administer the same set of items to an infinite number of individuals. Okay, so that we can get rid of this practice and fatigue effect and all those things, all the other errors which can occur at any point of time. Now, even then, when we are administering these, these items to, this infinite number of people, we get an average, right? So that average is supposed to be the true score. However, when we are administering the same set of items to an infinite number of individuals, okay, and we are taking the average, assuming it to be the true score, this true score becomes hypothetical. Why? Because definitely there will be n number of different factors which will be influencing the situations, and therefore the scores of the individuals will definitely change. Okay, so maybe there can be a number of factors, like in the testing situation, maybe one of the individual is not feeling well, so that will affect his or her score. Another individual might have some exposure to the same items, so the person's performance will also be influenced. So in that way, different factors will influence, and hence it becomes very difficult to obtain the true score in any case. Right. So here, this true score T that we are seeing here, it is actually a hypothetical score that we are talking about. And this random error consists of all the variances because of the other factors which might be affecting a testing situation. Together, this produce the raw score that we observe. So in a particular testing, if an individual gets a score of 10, suppose, maybe the true score for that individual is 8, and the additional 2 marks is because of the random error. Maybe some kind of exposure was there, maybe some kind of hint the individual got. Okay, and therefore it became 10. So that's how the classical test theory approach addresses the problem of this raw score that we get in any case. Now, for a very long period of time, we have been considering this raw score as a measure of all our assessments, right? Not only in ability tests, but also in any rating scale, questionnaire, anything that we are testing, we take the raw score as the indicative or indicator of an individual's ability or a particular attitude or a particular trait, whatever that we are considering. But there is a very, very serious limitation of this, considering the raw score as representative of the trait or ability. What is that? Well, let us consider this particular example here. We can see three different cups, right? The first one, the smallest, then this second one is a little larger, and the third one is the largest one. And we have a scale here. So if we try to compare the heights of these cups, let us see. The first one is basically 2 units here. If we consider the scale here, then it's 2 units. The next one is 3 units. Third one, 4 units. So now let us consider the difference of sizes of these cups. The first one and the second one, it differs by 1 unit. Again, second one and the third one differs by again 1 unit. So in that way, if we compare the first one, okay, with the third one, then this difference is actually just double of this difference. So we can think of it in terms of ratio, like 1:2, like that kind of a ratio, because this difference, the difference of height between the first and the third cup is just double of the difference of the height between the first and the second cup. So this is a physical measurement that we are doing, and this is what we call the linearity of the measurement scale, which is very much true in case of any physical measurement that we do. Right. Now, let us consider similar type of measurement in case of a psychological test. Okay. Let's consider this scale, this continuum here, and like the scale in the previous example. And suppose that the minimum score that can be obtained in this particular ability test is 0. The maximum score that can be obtained is 30. Now, we have in the first part of the set of items that are there, probably there are 30 items. So in the first part, we have items which are of low difficulty. Second part, which is of average difficulty. And the third part, which is of high difficulty. All right. So we have in the first part, the low difficulty items means they require low trait level to be solved. In the second part, average difficulty level items, they require average trait level to be solved. And the third one, that is the high difficulty level, requires the high trait level to be solved. Okay. Now let us consider 4 individuals, okay, who have obtained different scores. So we have Manas, Charu, Robin, and Jaya. Excuse me. Manas obtained a score of 4, Charu obtained a score of 12, Robin obtained a score of 20, and Jaya obtained a score of 28. Now, if we compare the differences of score between these individuals, Manas and Charu, the score difference is 8. Robin and Jaya, score difference is also 8. Just like the previous problem, right? But you see, the complication lies when we compare the difficulty level of the items or the trait level that is required to solve these items. For example, in the first case, Manas obtained a score of 4, which means Manas has very, very low trait level, and therefore is only able to solve the first 4 or 5 items of, he could attempt, but out of that only 4 were correct of the very, very low difficulty items. Charu, on the other hand, she is also having a low trait level, and she has been able to complete the first 12 items, most likely. But that also very, items of very low difficulty. On the other hand, if we compare Robin and Jaya, Robin was able to complete all the items of low difficulty. Also, most of the items of average difficulty level, okay, and therefore obtained a score of 20. Jaya, on the other hand, could solve low difficulty items, average difficulty item, and also most of the high difficulty items, and therefore obtained a score of 28. Right. So although the difference between Manas and Charu, that's of 8, and Robin and Jaya, that is again of 8, it's same, but the trait level that is there for each of these individuals, it's different. Very, very different. Okay, and not comparable at all. All right. So therefore, although we have a similar type of scale that we are considering here, but it becomes very difficult to compare this ability level based on the raw scores. The reason why I'm talking about this ability testing is because item response theory was primarily built on ability testing. The item response theory models of rating scales, it came on later as extensions of the ability testing models, right? All right. So the summary of this discussion is that when we are comparing raw scores, when we are considering the raw scores and trying to compare individuals on the basis of this raw scores, it can be extremely erroneous if we do not consider the underlying trait level that is required at a particular level to solve a number of particular number of items. All right. Taking an example from the Bake Depression inventory, something that we, all of us, we know about, right? Now, Bake Depression inventory, the first part of first version of Bake Depression inventory actually was, constructed using the classical test theory approach. All right. And back at that time, the raw scores were considered. So the problem that individuals face because of this is what we are going to discuss here. You see, in the Bake Depression inventory, we have these different items, and each of the options that we are seeing here is actually taken as 0, 1, 2, 3, like that. So if the individual chooses, I do not feel sad for the first item, maybe I do not feel sad, so the person gets a score of 0. If the person chooses, I'm so sad and unhappy that I can't stand it, the person gets a score of 3 in the first item, like that. Now, let us consider two individuals. Both of them obtain a score of 20, for example. Okay, so it means that there are different combination of scores which the persons they had obtained in across the different items. Now let us consider item number 9 that is there, which basically measures the suicidal ideation. So here the options are like, I don't have any thoughts of killing myself, that's 0. I have thoughts of killing myself, but I would not carry them out, 1. I would like to kill myself, 2. I would kill myself if I had the chance, 3. Right. So it is possible that among these two individuals that we are trying to compare, the first individual probably has got a score of 0 in the 9th item, but probably has scored higher in the other items and therefore got a score of 20. On the other hand, the second individual got a score of 3 in item 9 and other different scores in other items and hence got a score of 20 as a whole. But we are taking both the scores to be at the equal level, 20, for both of them, we are giving the same diagnosis. But one of them is having suicidal ideation, the other one is not having suicidal ideation. All right, so that complicates the situation. Okay. The complications here are that this traditional method of scoring assumes that each item or symptom on the scale represents comparable level of trait or severity. So when we are comparing, say, I'm so sad and unhappy that I can't stand it, and we are giving a score of 3 for the first item, and again we are comparing maybe the fourth option in any other item, like I feel I'm being punished, and also giving 3. Okay, we are considering both these items to be at the equal level, but it may not be so. All right, we might not know if we consider only the raw scores for this scoring approach. Also, it assumes that each item has identical properties across samples. So BDI, when it was first constructed, there was this complication because we need to have, in such kind of cases, we need to have too many different norms for each of the different tests and the samples to which we are administering those tests, right? So the basic assumption here is that all these items will behave equally across different samples. Well, that also becomes a problem. Let us consider this item number 10, okay, of BDI. I don't cry any more than usual. I cry more now than I used to. I cry all the time now. I used to be able to cry, but now I can't cry, even though I want to. Now the thing is that in certain cases, this crying behavior is different across different societies. There are certain societies which do not encourage the behavior of crying. All right, so in such kind of societies, this particular item may not give you the kind of the desired response that we want, right? So it becomes difficult when we are comparing different societies, like for example, the Asian society with the Western society on the basis of an item like this, and we are concluding the same kind of inferences. That becomes a problem. Again, two individuals having the same score can differ in terms of relative severity and frequency of different components of psychopathology. As I explained, that two individuals might have same score, getting same diagnosis, one with suicidal ideation, the other one without suicidal ideation, right? Also, the distance between different options that we are considering, okay, in each of these items, it's not the same as the distance between the other ones. All right, so if you're considering this, the distance between I do not feel sad and I feel sad, okay, from not being sad to yes being sad, the distance between these two and the distance between I'm sad all the time and I can't snap out of it, and I'm so sad and unhappy that I can't stand it, these are considered to be equal in the classical test theory approach. But how can we say that these are equal? Because these are extremely, non-numerical qualitative items that we are talking about, qualitative statements. Okay, so that again becomes a major complication when we are considering the classical test theory approach, right? So because of this, the psychologists, psychometricians, they started thinking about an alternative, and that's how the Rush model of measurement first came into the picture. It was proposed in 1960s. Okay, so I will now start with the Rush model of measurement, what it talks about, and what's the basic theory, underlying theory in the Rush model of measurement, right? So if you have any question, you can just write it down in the chat box, and I'll be able to answer. All right. Okay, so let us consider the discrimination index that we measure in case of classical test theory approach. Okay. we know that discrimination index here is basically the correlation between the scores on an item and the total score on the test. Okay, that is an indication of the item's discrimination. All right, in simple terms, the item total correlation that we are talking about. Also, there is another way in classical test theory approach, we use another way to measure the DI, which is where we categorize the total number of persons into different groups based on their total score. All right, so the lower third, the middle third, and the upper third. So let us consider this example here. I hope it is visible to all of you. Let us suppose that the question is, the capital of Madhya Pradesh is A, B, C, D, Jabalpur, Indore, Bhopal, and Raipur. Right, now, suppose the total number of respondents answering the item is 120. So after you get the responses, you divide this entire 120 individuals into 3 groups based on their scores. So the lower third are those 40 individuals who got the lowest scores. Then the middle third, okay, middle 1/3 who got the average scores, and the upper 1/3 who got the highest level of scores. Okay, 40 in each of these groups. Now, let us compare the upper and the lower group on the basis of the responses which they gave for this particular item. All right. So the let's see. Here the correct answer is option number C, that is Bhopal. So let's see what is the number of individuals who answered the upper group, in the upper group or in the lower group. In the upper group, only 1 person chose option A, 2 people chose option B, 36 people chose option C, and only 1 person chose option D. All right. In the lower group, 8 people chose item A, okay, option A, 15 people chose option B, 7 people chose option C, and 10 people chose option D. All right, so the discrimination index is therefore calculated as, number of individuals who chose the correct option in the upper group minus number of individuals who chose the correct option in the lower group divided by the number of people in each of these upper and the lower group. So in both upper and the lower group, we have 40 individuals. So it stands like 36 minus 7 divided by 40, that's 0.725. So 0.725 is the discrimination index of this particular item. Right. So that's a very, a very good method, very popular method of understanding the discrimination index of each of these items. Also, it tells us a lot of things, for example, whether all the options are working fine or not. Because if we see that maybe one of these options is not chosen by any of the individual in the entire group, then that option is a dysfunctional option. So you need to modify it. So it is important that at least one individual from each of these groups should choose each of these options. Otherwise, that option may be dysfunctional. Also, it tells us that whether a particular item is working fine or not. For example, here we see that in the upper group means individuals having the higher ability, 36 of them were able to answer the item correctly. Right. In the lower group, 7 people could answer it correctly. Others actually got it wrong. 33 of them got it wrong. All right. So which is very obvious, because in the lower group, we have individuals of lower ability. So for them, it becomes difficult to answer the item correctly. Right. So that's why we see this discrepancy. So this is absolutely fine. But what if it is the other way around? So you see that in the upper group, many people got it wrong, and in the lower group, many people got it right. That should not be the case. right? So if that is the case, then you have to think about it. You have to either reject the item or modify the item in some way. All right. So that's why it's a good measure of discrimination index in classical test theory approach. Now, consider this. Therefore, a similar type of example, if we consider, you see, the x-axis, it's the lower, middle, and the upper group, as you know, the similar way, in which we estimate the discrimination index. So you have the lower, middle, and upper group. Their group means are there. Okay, and on the y-axis we have the proportion correct. So proportion of people who got the answer correct for item 1, 2, 3, and 4. Right. So by just by looking at it, what do you think? Which is the easiest item among all these 4 items that you can see here? Anyone? Can you answer?
Yes, item number 1.
Yes, absolutely. And the hardest one?
Item number 4.
Right. You see, very easily we are able to answer these questions. If we consider item number 2 and 3, you see in the lower group, most people could answer item number 3. It's the proportion is higher. 60% of them could answer, 40% could not answer. But as we go into the middle and the upper group, it became reversed. So in the upper group, almost 90% could answer the item number 2, but almost 80% could answer item number 3. All right, so this type of a graph actually gives us a good understanding of the discrimination indices of the items. So to what extent the items are able to discriminate people with respect to their trait level, right? Now, consider more than 3 class intervals.
Ma'am, just a minute.
Yes.
Ma'am, sorry to interrupt.
Yes.
In the how do we find the trait level? By summing all the questions answers or any other way?
In classical test theory approach, we do not consider the trait level as such. We consider the raw score and we compare individuals on the basis of that raw score. That's it. Okay. So discrimination index tells us about whether the item is working fine or not. But as a whole, in the classical test theory approach, we do not consider item-based analysis. We consider the total score and we compare individuals on the basis of that total score. That's how it is done. Okay.
No, my question was that how we I could not get how we find the trait level of the individual, whether it belongs to lower or middle or upper?
Yeah, trait level is because no, it's absolutely fine. Trait level is because definitely individuals who are at the lower 1/3 of the individuals, as you can see here, means their total score is at the lowest level. All right.
Okay.
So total score is at the lowest level. Lowest level means they could answer only a handful of items. Most of the items they could not answer. So it means that their trait level is lower than the other individuals.
Yeah, thank you, ma'am. I got a point.
Okay.
Thank you so much. Yeah.
All right. So let us now consider that suppose each of the total score, each of the score is considered as a class interval. So we can consider an example where suppose a large number of individuals have been administered a number of items. So suppose there are 18 items, okay, which is measuring some kind of proficiency test, and it has been administered to 10,000 individuals, right? So in such a case, it is very obvious that maybe a few hundreds or thousands of them got a score of 1. Again, a few hundreds or thousands got a score of 2. Okay, a few hundreds or thousands got a score of 3, and so on till 18, right? So each of these scores can be considered as one class interval in such a case. All right. So therefore, if we try to put all those in a graph, it appears something like this. So you see in the x-axis we have total score of 18. So there are, from 0 to 18, we have 18 different class intervals that we are considering. And on the y-axis, we have the proportion of positive responses. What is the proportion of correct response that we have got for each of these class intervals, right? Now let us consider these 4 items again, item number 3, 7, 11, and 15. So you see, how can we interpret for the item number 3, which is probably the easiest one here. If you can look at it, you can understand this is the easiest one. Why? Because you see, item number 3, almost 18% of the individuals got a score of 1. Okay, almost 40% of the individuals got a score of 3. Who got a score of 3, they got it correct. This item number 3 correct. And it reached almost 90% of them got it correct. Those who got a score of 10. So individuals who got, a score of 9 or 10, total score in the entire test, 9 or 10 means almost, at the average level. Their trait level is average, but all of them could, answer the item number 3 correctly. All right. So for item number 3, proportion of correct response reached almost 90 to 100 by, total score 9, 10, 11, 12, like that. All right. So individuals having a trait level equivalent to a total score of 9, 10, 11 out of 18, they got the item number 3 correct. All of them got it correct. Right. So it means that item number 3 requires very less trait level to get it correct. So anyone with a low trait level can also get it correct. On the other hand, if we see item number 15 here, you see item number 15, the 100% correct for item number 15 was achieved by only those individuals who got a total score of 17 or 18. All right. So only those individuals who got the highest score, okay, almost a full score, 17 or 18 out of 18, only they could get the item number 15 correct. Most of them got it wrong. Okay, if we compare the 50% correct also, the proportion 50%, then also the total score stands at 14 or 15. So out of 18, those who got 14, only, among those also, only 50% could get the item number 15 correct. All right. So it actually shows that item number 15 is actually a very difficult item, right? So this is how we can understand whether a particular item is falling at a lower trait level or at a higher trait level. All right. Now, if we consider this continuum abstracted to a true score, so it is a raw score that we are getting here, the total score that we are getting, possible total score. If we take this total, possible total score, this continuum as the true score, okay, which is actually a hypothetical, it's a theoretical understanding, okay, and the proportions are, it becomes, when it is abstracted to true score, the proportion here also becomes theoretical, so they become the probability. So when we take the true score in the continuum, all right, and we take the sample size to be like an infinite size, then the proportion of positive responses, that becomes our probability of giving a positive response, because the population becomes infinite in this case. All right. So these are the probabilities that a person of a given true score will respond positively to an item of particular difficulty. Instead of total score, the true score is located on the horizontal axis, and instead of the observed proportion of persons with a positive response, the probability of a positive response is plotted on the vertical axis. So when we take it at this level, at an abstract level, then we get this sort of a graphical representation, where you see that the x-axis becomes the true score as in classical test theory, right? And the y-axis becomes the probability of a positive response. So how can we interpret this part then? You see, it remains the same almost. In the x-axis, instead of now the 0, 1, 2, 3, 4 till 18, it now becomes, the logits that we get here. So -5, -4, -3, -2, -1, 0, and then 1, 2, 3, 4, 5. Okay, these are the logits. Okay, and the equivalent level of true score, total score, you can see here 10, 11, 16, 17, like that. Okay, and at the y-axis, we take the probability. So when we take that, yes.
Sorry, just a minute.
Yeah.
In this graph, the x-axis, how this -4, -3, -2 came? I could not
No,
get it.
when we take it as a true score. So since true score is an abstract concept, okay, it's a theoretical, it's a mathematically, derived type of continuum that we are considering here, considering the population to be infinite. Okay, it's a hypothetical assumption. Till here, before this, we were considering a finite population, that is 10,000 individuals, and we had proper counts. Okay, that out of 10,000, maybe this number of people scored 1, this number of people scored 2, like that. Okay, but when we take it to the infinite level, okay, then it is possible to assume that we can take it as an equivalent to a population, huge population. All right. And in the population, then the occurrence of a particular event, like a positive response, then it becomes the probability. Okay. All right. Okay. Okay. Yes. So therefore, it becomes the person logits. This this is just same as the normal probability curve. If you can think of it, if you fit the normal probability curve for an infinite population, which is a mathematical distribution, it's the same thing, isn't it? So so that's how you get this x-axis here. All right. So this is the true score, equivalent to true score in the classical test theory approach. Now you see the same thing for item number 3. You see, we get a smoothened curve here because we have this huge infinite population and we are plotting probability, not proportion. We get a smoothened ogive or an S-shaped curve for each of these items. Right. So same thing you see for say for example, item number 15, individuals who got a raw score of 16. All right. They among them, almost 80% of them got this item number 15 correct, and 90% of individuals who got a score of 17 got the item number 15 correct. Okay. So here also we are able to understand which of these items are the easiest one and which of these is the difficult one. Right. I hope this is clear to all of you. Okay. So
concept is clear, but on the x-axis numbers -5, -4, -3, how it come? I couldn't get. Concept I understand.
That's because sir, when you are, say, if you're considering the simple proportions, all right, proportion is all right when your population is finite. Okay, the number is known to you. Okay, so when you are tossing a coin, maybe twice, okay, how many times heads, how many times tails you are getting, that's fine. But when you are doing it an infinite number of times, then we take help of mathematical understanding, right? We use binomial equations to derive the number of times the heads and the tails will come. And if you plot all those, derived from this binomial equation, if you plot all those, you get the normal probability curve. Right. And since it's an infinite population, therefore this it is denoted by these -5, -4, -3, 0 to +1, +2. So you have a positive domain and dimension, and you have a negative dimension. In normal probability curve, as we know that 0 is the basically the mean of the population, right? Yes. And the each of these are the deviations, 0 to 1, 1 to 2. These are the deviations.
Okay.
Okay, so here also it's almost the same thing, but here the purpose is different. Here these numbers are used to denote the person's location on the continuum, okay, in comparison to the entire population. Okay.
Okay.
All right. So this is actually, this, you see, this is something that we derive from the classical test theory approach only, right? It is not something that we have, we have taken from some other concept. We have just taken the, way in which discrimination indices are measured in classical test theory, and we derived this, this type of a distribution, right? But this is actually the basis of the Rush model of measurement. Right. So what happens here is that Rush model of measurement is actually a probabilistic model, and a probability is, it can be considered as a theoretical abstraction of an observed proportion. Okay, probability is actually mathematical. All right. So modern test theory models actually focus on the engagement of a person with an item rather than the total test score of a person in classical test theory approach. So till now, we were talking about the total score obtained by an individual in a particular test, right? Now onwards, we will be talking about the interaction between a person and an item. Okay, so why? Because Rush's model, it talks about a two-way frame of reference. Okay, so it talks about the kind or class of items, okay, which are governed by the construct that is being assessed. And it talks about the kind or class of persons who are relevant to be assessed, right? So it is very obvious when you are testing an individual, there are two things which we are considering. One is the item that we are considering, and the other is the person to whom we are administering the item, and we are seeing the results, right? So there is an interaction of this person whom we are testing and the item which we are using for the testing. Okay, and also the conditions of the administration of the instrument. So if we consider in this way, this is the two-way frame of reference that was given by Rush. So it talks about the location of person and location of item. How does it do? So if we consider the response X, say small x, then he says that this small x is actually a function of the item's location and the person's location. Okay, so item's location is denoted by A1, A2, A3, AI, and so on. And the object's location is denoted by O1, O2, O3. Object means here the person's location is denoted by O1, O2, O3, like that. So an item, a response that is generated here is basically an interaction of this item number A1 and the person number O1. Okay, so that's why we see that maybe the same item has been correctly answered by one individual and incorrectly answered by another individual, right? Because the item response theory assumes that each of these response, okay, specifically in rating scale, we see so many different combinations of responses from the individuals, right? Because the Rush model, that's why the Rush model assumes that any of these responses is actually a function of the item, okay, difficulty or severity that we are talking about, and the person who is being measured at any point of time. All right. So on the basis of this, we talked about the this interaction between the person and the item to produce the response that is there. Conceptually, it is not much different from the classical test theory approach that is there. Okay, but in classical test theory approach, the one difference that we find is that there is no concept of item location parameter. Okay, the item location that we are talking about, where an item is located. For example, here we are able to say, okay, this item number T, where is it located? towards the left end of the continuum, while item number 15, which is a difficult one, is located on the right end of the continuum. So we are able to locate a particular item on the continuum. This understanding is not being considered in classical test theory approach. All right, so that's the kind of problem that we see there. In item response theory, we consider this in addition, and that's why it produces something where we see that response is always a consequence of the item's location and the person's location. So they say that the response of person N to item I is denoted by X and I. And in the dichotomous response case, where it can take two values, X and I can be 0 or 1. 0 means incorrect response, 1 means correct response. So the parameters, that is beta N and delta I, it can take on any real values that can extend between -infinity to +infinity. So if comparisons are to be made between persons in terms of their parameters and between items in terms of their parameters within a frame of reference, then the structure of the responses should be that, number one, comparison between any two persons is independent of which subset of items in the frame of reference is chosen for making that comparison, and independent of any other person that might be compared. Number two, comparison between any two items is independent of which subset of persons in the frame of reference is chosen for making that comparison, and independent of any other item that might be compared. All right, so here, since we are considering the items location separately and the person's location separately, this comparison of two persons or comparison of two items is independent of any other parameter that we are considering, which was not true in case of classical test theory approach. All right,
Sorry,
there, yes.
What is the parameter Bn and delta I?
Beta N and delta I, these are the this person's location is the beta N and delta I is the item's location.
Okay, thank you.
So this comparison actually tells us that, it is independent of any such things. In classical test theory approach, the problem is that, when you are considering, say, for example, 10 items you are taking and you are administering it to a group of, students, maybe 100 students in one school. All right, maybe the school is, comprised of students who are maybe, not very high ability students are there. So there you will find that the items are quite difficult for them. All right, so you will conclude that the items are difficult items, right? Now you take the same set of items and you go to a second school, where probably the students are of higher ability, and you give it to them and they can very easily answer the items, and then you have to conclude that the items are easy ones. So which one will you do? So you see the problem in classical test theory approach, when we are constructing a test, the items become very much dependent on the persons to whom you are administering the items, as well as the trait level of individuals. If you are comparing individuals, the problem, because the items are very much dependent on us on the sample which you are considering for the construction and validation purpose. But in Rush's model, since we are considering the location of item and persons separately, it's not at all dependent on any of these different parameters that are there. Okay, so you can very easily compare. You see, these are the continuums. These are the continuums means the trait levels, if we say. So you can see, for example, the first continuum, if we consider, these are this delta 1, 2, 3, 4, 5. These are the item locations. So we have 5 items, okay, located at different positions across the continuum, and the person's location is here, beta. Okay, so which of these 5 items will the person be able to answer, and which of these he will not be able to answer? Can anyone Tell me.
He can do the delta 1 and will be difficult for delta 5.
Right.
Is it?
So yes, so item number 1, 2, 3, he'll be able to answer because his location is after these. So he has higher ability, all right, and therefore he'll be able to solve these 3 items. But he will not be able to answer delta 4 and 5 because the locations are on the right side of his location. So, these 2 items will require higher ability to be solved. All right. Similarly, in the, say, for example, the third item, if we consider, okay, how many of these items will he be able to answer?
All 5.
All 5. All right. In item number 6, if we consider, there are 2 individuals, okay, who is having higher ability level?
Beta 1, first one.
Beta 1. Thank you very much, sir, for your answers. I would like to hear answers from the other participants as well. So if you are able to understand, please try to answer these questions because this actually forms the basis of item response theory. Right. So in this way, we can, have this continuum and, similarly, we have this item location, person location, and we are able to understand whether an individual is able to answer the item or not. Okay. And since all these locations are based on the true score, means they are mathematically derived. These are person logits that we are seeing here. Therefore, it is not sample dependent. You give it to any sample across the world, you bring them here, this kind of a continuum, you place them and you can directly compare them across the items. All right, that's the advantage of the item response theory.
Ma'am, the last sentence that you spoke,
Yes.
sorry. Yeah. What is the purpose of all this?
Purpose is that,
Yes.
Suppose you have developed a particular test, right?
Okay.
So, sir, from which state do you belong? You are from?
I'm currently I'm in Jamshedpur, Jharkhand.
Jamshedpur, Jharkhand, right. So probably you have developed a particular test. Of course, you take the local people as your sample, right? And you have developed the test. If you have used classical test theory approach, then if I want to administer the same test here in Bengal, I will have to adapt your test first. Okay, because for the Bengali people, it will not be a proper measure because it has been developed using the sample characteristics of Jharkhand. Okay, and you have not standardized that.
Okay.
Okay, but if you use item response theory, then the same test can be used here. Same test can be used in US population, Australian population, Japanese population, wherever you go. Not a problem.
Okay.
You got my point? That's the advantage of item response theory. So the tests which I have developed in, sir knows under his supervision, I developed this test, okay, by collecting data here, but I used item response theory, and that's why the same tests are now being used by people across the globe. So I get requests from USA, I get requests from Germany, okay, from India, different places of India. They mail me asking for, the test and the permission that, they can use it for their own sample. And it is a valid one because it has been developed using item response theory. That's the advantage of this approach.
Okay.
Right, sir?
Yeah, thank you.
Okay.
Thank you. Congratulations for that development also.
Thank you, sir. All right. So therefore, this Rashus model is actually a mathematical model for dichotomous responses. Initially, it was developed for dichotomous responses only. In 1960s, it was proposed. This Rashus model was proposed, and it assumes that when a respondent answers an item, this relationship is expressed by the natural log of the respondent correctly answering the item divided by the probability of the respondent not correctly answering the test item. Okay, I have not included the derivation of the Rash's equation because that's the mathematical or the technical aspect of it. Rather, I would like to, because the time is short, I would like to focus on the the concepts and the features of this item response theory. So this one considers two aspects, that is the location of the test item and number two, location of the respondent along the trait level. And this one allows the researcher to use a respondent's raw test score or scale scores and express the respondent's performance on a linear scale that accounts for the unequal difficulties across all test items. So now if you have developed the, yes?
Sorry, in first point, location of the test item along the trait level or the difficulty level?
Trait level. The continuum is the trait level. Okay, location of the item is the difficulty parameter.
Okay. Yes, got.
All right. Okay, so if using the item response theory, if you have developed a particular test, then you can directly compare the raw scores, because now the raw scores will indicate the person's location on the trait level. Okay, unlike the classical test theory approach, and that's why it is much more popular and widely applicable across different samples. You can directly compare different samples. For example, the BDI, the second version which was published, that was done, the revisions were done using the item response theory, and therefore the BDI can now be applicable across different samples across the globe. Not a problem. All right. So let's just take a look into the assumptions of IRT here. So the first assumption is that of what we call the monotonicity. Okay, what does this monotonicity means? It says that as the trait level increases, so does the probability of endorsing an item. Okay, this one is expressed as an S-shaped curve between the latent trait level and the probability of response to the item concerned. Basically the same thing that we talked about, the graphical representation that we talked about, this S-shaped curves that we get. So in item response theory, each of the item is expressed as an S-shaped curve, okay, like this. So this is actually a progressive curve for each of the item, where the x-axis is the trait level and the y-axis is the probability of a correct response. All right. That's the first assumption.
Latent trait?
Latent trait is any trait which you are measuring. It can be intelligence, it can be personality, it can be depression, it can be anxiety, attitude, whatever.
Okay.
Okay. Achha. Next assumption is that of invariance. Invariance in ability level and item properties across different samples. It means that item properties measured in a particular sample remain indifferent to sample characteristics like age, sex, etc. If you have considered IRT for developing the test, it means that the item properties like the difficulty index, discrimination index, etc., these become invariant across different samples, irrespective of the age, sex, socioeconomic background, culture, whatever you consider. Okay, that's the property of invariance. Third property is that of unidimensionality of the latent trait measure. It means that item response theory assumes that the construct which you are measuring, that is unidimensional in nature. Means if we are measuring intelligence, okay, then all the items must be measuring the same type of intelligence. All right, and not different. For example, if we are considering, say, the test of Raven's progressive matrices, suppose SPM we have considered. Now in standard progressive matrices, we know that all the 60 items are measuring the same trait, that is fluid intelligence, right? So in that case, you can apply IRT directly. Okay, such type of test constructions you can apply IRT directly. But if you have a test like that of the WAIS, okay, Wechsler's Adult Intelligence Scale, there we have different subtests. So if the test which you are trying to develop, it is having different subtests, then you have to apply IRT separately on each of these subtests, okay, because it assumes that of unidimensionality. If you have items of multi dimensions in the same set, then it becomes problematic. So either you have to apply it separately for each dimension, or you can go for a multi-dimensional IRT analysis, okay. The fourth one is that of local independence, where it assumes that the responses are independent. So item responses are uncorrelated after controlling for latent trait. If we consider the latent trait, if we control the latent trait, then the responses, item responses should be, for each of these individuals, should be uncorrelated, independent of each other. Okay. If we see that there is local dependence, sometimes it happens that the items are constructed. That's the art of constructing an item, that you have to make sure that the items are independent of each other in all possible senses, right? So if we see that there is a local dependence among the responses, so one response is dependent on one response to one item is dependent on another response given for another item, then it can distort the item parameter estimates. It can cause the scales to look more precise than they really are. So their reliability will be extremely high. It can be spurious, okay, but it should not be such, because of that. Or, a large correlation between two or more items can essentially define or dominate the latent trait. So maybe you have 10 items and 2-3 items have so very high correlation among them that they tend to dominate the rest of the items. Okay, so that again, interferes with the construct validity of the scale. So then if the local independence is not there, then what can happen? The construct validity of the test will get affected. So these are some of the assumptions of IRT. Now coming to the the graphs. So in IRT, we have very, very beautiful looking graphs that we get. All right. And we use each of these graphs to, represent the type of estimates that we get in item response theory. Since it is extremely mathematical, sometimes it is difficult to understand the estimates just by looking at the numbers. So that's why we use graphs, right? So for example, this is the item characteristic curve, or ICC, that we talk about. And you see this is similar to the other graphs which we have been discussing so far. So it is an S-shaped curve that you see, and the x-axis is the theta, or the trait level. The trait level is taken as theta here, okay, and the y-axis is taken as the probability of correct response. So here we get the different item parameters. Okay, which are these item parameters? First thing is the item difficulty. Okay, so how do we get it? If we consider the 50% probability of getting a correct response for this particular item, so you draw a line from almost 0.5 till here, and you draw a perpendicular here. So this point where it is actually meeting the theta level, that defines the difficulty level of the item. Okay, so what does it mean? It means that this much amount of activity is required to solve this particular item. Okay, and that's the location of the item. Okay, this is why we say that the difficulty level is the location of the item on the parameter, on the continuum, because this one here shows that this much amount of ability is required to solve this particular item. All right, so it is located here. So that's the difficulty index of the item. Acha. The next one is the slope. The slope of this curve actually shows the discrimination index of the item. Okay, the discrimination of the item, how much it is able to discriminate among different individuals. And the third one is the guessing parameter, which you can see here. This one is the lower asymptote, and you have to see whether the item is originating from the from below the lower asymptote or a little above maybe. So it means that the pseudo guessing parameter here is 0.13. It means that 13% there is a chance of a probability of giving a correct response. The probability is 0.13, even if the individual is having very low trait level. So less than -4 means at this level it is extremely low trait level. But even at that extremely low trait level also, the person can have a 13% chance of getting this item correct only by guessing. Okay, so that is how we interpret these different curves. All right, so the theta represents the latent trait level, the A represents the discrimination level for the item, B represents the item difficulty level, and C represents the guessing parameter. Right. These are the different types of curves which you can try to understand and compare. So I just go into the second type of curve, that is the item information curve, which shows that the level of information that you can get about a latent trait ability that an item can give. All right. So for example, here you see there are 18 items and you get a curve, okay, full curve for 18 of these items. And if you compare these items, this pink curve, item number 14, it has the highest peak here, right? Also another item, that is item number 11, this one also has a very high peak here. So it means that this item number 14 and 11, they are giving you the highest amount of information across the continuum, while these one, like this is item number 8, okay, and item number 18, these are almost flat curves which you are seeing, and hence showing that the information that you are obtaining from these curves is extremely low. Information means the level of information that you are getting about the particular construct which you are measuring. So if you're measuring, say, for example, the fluid intelligence, then probably item number 8 and 18, which are flat curves, are measuring very less amount of this ability, and therefore they are giving you this kind of flat curves, almost negative discrimination. So these items are not good at all. They are not discriminating among individuals at all. Okay.
Ma'am. Hello.
Yes.
Hello, ma'am.
Yes.
How had been inferred that what are the mechanism to identify that these values, these questions or these items are not measuring the
that's because area. Yeah, that's because when you are getting this kind of flat curves, right? You see these curves, these are flat.
Yes.
Okay,
yes.
Almost flat. So this flat curves means the discrimination is extremely low. Discrimination means, as I mentioned, the slope of each of these curves. So it has to be an upward moving slope. Okay, not a flat curve or a inverse type of a curve. Okay, if it goes up, then it means that it is discriminating very well.
Yes.
All right. So that's why it is showing that it is not discriminating at all.
No discriminating power of these items.
Yes. Okay.
Yeah.
These are other examples you can see. And test information function, this is also another important curve that we get in IRT analysis. This one shows the type of discrimination that you are getting when you are combining all the items together. So it means that the total information that you are getting from all the items taken together. Generally, we expect a normal bell curve type of a curve here. All right. for example, this one, which you can see, it is a little skewed that you can see, but again, it's a bell curve, which means that, it is providing you the highest information just, at the above average level, it is giving you the highest level of information, right? As you go towards the extremes, the amount of information is going down, means the discrimination ability is going down. All right. But again, it depends upon a number of factors. Like if you are doing a testing for say, for example, here in our country, we have this, CAT examination for getting into management studies, or NEET examinations for medical entrance, like that. So in such cases, what happens? You select the best of the best, right? So in such cases, your items should be discriminating at the highest level of the continuum, right? So there you get skewed curves. So it depends upon the type of testing that you are doing, all right, and you have to interpret it accordingly. All right. So now coming to the IRT models, all right. Overall, we can think about the dichotomous, and it depends upon the dichotomous and the polytomous responses. Dichotomous means where you have binary response, 0 or 1, like as in ability testing that we do, right? So there we get 3 different types of models. The first one that was developed was the Rush model, okay, and based on the Rush model, the 1-parameter logistic model was established. And then the 2-parameter and the 3-parameter logistic model were proposed, which are nothing but extensions of the Rush model itself. All right, and polytomous responses, which we get for rating scales, for this type of responses, we have 5 different types of models that we get. Okay, we will be discussing these 5 models here. So item properties, difficulty level. I won't discuss the that for the binary response, because that we have already discussed. If the ability is higher or lower, the difficulty of the items change accordingly. But what if we are considering rating scales, right? In rating scales, there is no such thing as a correct answer or a wrong answer. All the answers are, they give the answers as appropriate for them. So there is no right or wrong answer, and hence there is no concept of item difficulty. But here it implies the probability of endorsing a particular response category for a particular item. All right. So response category are the different categories that you have. For example, if you are taking a 5-point Likert scale, then you have 5 response categories, right? Now, the probability of endorsing a particular response category across these 5 response categories, that is the difficulty level that we consider for rating scales. All right. Now it is very much obvious that, for example, if you take the scale measuring extroversion, suppose extroversion personality trait, then it can have 2 different options. Say, for example, the first one is I enjoy having conversations with friends, and the other one is I enjoy speaking before large audiences, right? Now, both items are measuring extroversion, but the first item is more likely to be endorsed at the highest level in comparison to the second item. So anyone who is an extrovert will be giving a, maybe a strongly agree for the first option. Okay, I enjoy having conversation with friends, because all extrovert people would love to enjoy having conversation with friends. But if we consider the second response option, that is I enjoy speaking before large audiences, probably a less number of individuals will endorse this option. Why? Because not every extrovert person will enjoy having to speak before large audiences, even though we have, many of us, we are extroverts, but we do not enjoy, speaking before large audiences. Only some of us can do that, actually. So, that's how this probability of endorsing a particular option vary across the response categories. All right. And that's what we measure under the difficulty parameter in IRT for rating scales. All right. And these are the ranges that we considered Okay, above -2, it's very easy. Between -2 and -0.5, it's easy. Between -0.5 to +0.5, it's medium. Between 0.5 and +2, it is hard, and above +2, it is very hard. Item discrimination, this is also
On
something
a
that
5-point
we have.
scale, remember?
Sorry.
It was on a 5-point scale, I think.
Yeah. In the as per the continuum. It can be, it is not like a 5-point scale. It is like, generally it gives you a continuum between +4 and -4, but it can be anything more than +4 or anything more than -4. It is actually -infinity to +infinity, the range.
Okay.
Item discrimination, we have already discussed, so I'm not going into the details again. Just criteria, it is there in the slide, so you can refer it from the slide. Only one thing that we have to make sure that if there is a negative discrimination value, then the item is a problematic one. Okay, so you have to reject it or modify it, definitely. All right, so comparing the classical test theory and the IRT, why should we go for IRT? Well, I have I think I've given you enough reasons to go for IRT now, but there are studies which suggest that if in classical test theory also, if you can take proper precautions and use a random sample and then go for the item parameter estimation, then it will probably give you a similar picture to that of IRT. Although the more complicated understanding of items you will not be able to get in classical test theory approach, right? So these are the dichotomous models that are there: 1PL, 2PL, and 3PL model. Very simply, the 1PL model includes only the difficulty level, only the item location it considers, and assumes the discrimination value to be constant across all the items. In 2PL model, we consider both item difficulty and item discrimination, and we take both of these to do the item parameter estimation. And in 3PL model, we consider the guessing factor, which is the third parameter, and these are applicable only for ability testing. Okay. Coming to the rating scale models, their IRT models include, there are 5 different types: the partial credit model, generalized partial credit model, graded response model, rating scale model, and the nominal response model. These are the five different models which we consider. Okay, let's see each of these. So these are the mathematical expressions that we use for these, nothing but an extensions of the Rush model only, with some specific features of their own for each of these models. All right, here going into the details, instead of the item characteristic curve, here we get the category characteristic curve. All right, so category characteristic curve means, for example, suppose there are 5 response categories you have for a rating scale: almost always, mostly, sometimes, rarely, never. All right, so if you plot this item characteristic responses here, you get category characteristic curve like this, where you see that the first and the fifth response category generates these type of slopes, while the middle 3 categories generate these type of slopes. All right, so if you have 5 response categories, you get 5 different slopes like this. All right, if you have 4 different response categories, you will get 4 different types of slopes like this. All right, it depends upon the number of response categories that you have taken for your item. Partial credit model and generalized partial credit model. The PCM is the simplest type of IRT model for polytomous responses, okay, with 2 or more ordered response categories. Okay, 2 or more ordered response means where you have a 3-point rating scale or 4-point rating scale, 5-point or 7-point, whatever. It's just an extension of the Roche model. And here you have only 2 sets of parameters. One is for the person, one is for the item. So it's an extension of, you can think of it as an extension of the 1PL model, where you are considering only the difficulty level, that is the item location, and that's it. The discrimination is taken to be constant for all the items. All right. On the other hand, the generalized partial credit model is a 2PL extension of the PCM, where you are considering 2 parameters together. One is the difficulty level, that is item location, as well as the discrimination parameter as well. So you take these 2 together in the generalized partial credit model. So if your responses are polytomous, as in the rating scale, then PCM is the 1PL model, extension of the 1PL model, and GPCM is the extension of the 2PL model. So in PCM, you consider only the item location for your items, okay? And in GPCM, you consider both the item location as well as the discrimination ability of your items, okay? Can compare these, okay, more or less they will give you the similar kind of results. However, in PCM, you will get only the difficulty estimations. In GPCM, you get both the difficulty and the discrimination indices. Here, I'll just show you the R Studio, although this workshop is not on R, but also we have very less time remaining. So I'll just show you a little demonstration here, and then I'll go back to my slides here. So I have provided all the scripts. I hope you have received the scripts along with other resources. Maybe Ruchira can confirm. Ruchira, was it shared with participants?
No, ma'am, we'll share it after the presentation is over.
All right. Okay, okay. Fine. The scripts are all there, so you can run the scripts to generate the outputs for your IRT models. Just have to install the packages in R, and then you can do it very easily. I have also provided the scripts for the polytomous IRT, and you can start running each of these scripts. So since it was not provided before the workshop, so it's not there with you, so you can't run. So I'll just explain it to you from the slides that are there. All right. So in the partial credit model, you can simply, if you run the scripts, it will generate the this kind of estimates. Okay, these are the estimates that you get. So you have 10 items which are basically that of a rating scale. All right, and these items, these are the category characteristics that are there, basically the location of each of these response category that are there, and the discrimination is taken to be constant across all the 10 items that are there. Okay, that's for PCM. Similar thing you get for GPCM, but in GPCM, since it's extension of a 2PL model, you consider also the discrimination indices, and therefore you get the discrimination indices here as well. Okay. If you compare the graphs that are there, you get beautiful graphs there. These graphs are for the PCM and these for the GPCM. Just one thing I'll just mention here. While interpreting these curves, you have to be careful about the redundancy in the response categories. What happens here is that sometimes we include responses which are not required. Okay, response categories which are not required. For example, suppose you have a 5-point rating scale and you have included response categories like not at all, slightly, very less, moderate, high. Okay, now this slightly and very less, these two categories are almost same, right? It depends upon the type of item which you are presenting. You have to understand whether each of these response categories are functioning well or not. All right. It is possible that the respondents have not chosen any of those response category because it is not applicable for them. For example, once I had got this kind of a data set where there were 5 response categories, 1, 2, 3, 4, 5, and I wanted to apply a GPCM model there, but every time I was trying to run it, it was showing me error. So I was not able to understand what is the kind of problem that is there, because everything else is fine, so it should run. But then I looked into the data and I found that the respondents, none of them actually chose the response category 1. All of them chose 2, 3, 4, 5. So it was very much possible that the response categories 1 and 2 were almost the same. So category 1 was redundant for them. So that's why they did not choose the category 1 at all. All right. So that's a major problem. If you have taken a response category which is redundant, okay, not essential, not necessary, then what will happen? It will be an extra baggage for your test, and it will interfere with all the item parameters which you'll be trying to look at. Okay, so how can you answer this redundancy? For example, here you'll see that some of these curves are all overlapping. If you have this kind of overlapping curves, for example, here, response category number 1 and 2, these are highly overlapping, you see. Okay, both in PCM and GPCM estimation, you see that category 1 and category 2, they are almost same. Okay, so it means that the category 1 is redundant. So you can just do away with category 1 and you can keep it precise with 4 different categories. That will also serve the purpose. Right. So this kind of an interpretation will help you understand whether all the response categories which you have included in your rating scale, whether all of those are functional enough or they are redundant in some sense. All right. Okay. PCM versus GPCM I have shown, although it is not, it is necessary sometimes, because sometimes we have to make a decision about whether we want to go for a, 1 parameter model or a 2 parameter model. So, if both of those different types of models fit your data, it is better that you can compare these 2 models by looking at the log likelihood. So the smaller the value, the better the model. Okay, so you can make a decision based on that. But it is always good to go for a 2 parameter model, because it explains a lot of variances, because it considers a discrimination level as well. Okay. Graded response models are the third type of model that we have. This is also an extension of the 2 parameter model, and it's almost the same as the GPCM, although there are certain conceptual differences that are there. But graded response model is a very, very popular and widely applicable model that we have. So GRM also, gives you such kind of graphs, so you can apply both GPCM or GRM. Okay, it's fine. It's applicable for all the Likert scales that we have. Both GRM and GPCM are applicable, so it's absolutely fine. Graded response model also, this gives you. Here it is known as extremities or boundary characteristic curves you get. So these first 4 columns, that gives you the item location, means the location of the response categories. And this last column here gives you the discrimination indices of these items. So the same 10 set of items that have been used for the GRM estimation, you get the discrimination indices. It shows that all the items are discriminating very well, actually. So you interpret the values like that, and also you interpret the curves for the same. Okay, these are the curves. So overall, it gives you a good estimation, although you have to look for the redundancy in the response categories, as I mentioned. GPCM or GRM, again, is the same thing. It depends upon the type of scale that you are using. You can apply both, and then you can compare. You can look at the lesser value of the log likelihood ratio, and you can choose accordingly. Okay. Rating scale model is also same as PCM. Okay, so it is also a one parameter model extension for polytomous responses. But one significant difference that is there for RSM and PCM is that a partial credit model can be applied even if the response categories are different for different items. Okay. I'll show you one example where these two are, differently it can be applied. So there are certain scales where sometimes we need to have different types of response categories for different items. In such cases, the rating scale model is not applicable. There you can apply only the partial credit model. Okay. Rating scale model, on the other hand, is applicable only if all the items in the scale are measuring the same thing, okay, in the same framework, then only you can apply the rating scale model. So rating scale model estimation can be done using this commands here, the scripts that I have provided, you can use those. And here also you get different category characteristic curves. You can estimate the percent parameter using this type of estimation, the conditional maximum likelihood estimation you can do, and you can get the percent parameter plot. It means basically it's a very useful plot that you can get, and it shows you that according to the raw score, what is the theta level. Means, if someone gets a raw score of 25, suppose, what is the equivalent level of, trait that the person is having. So, for example, if someone is obtaining a score of 20, okay, the corresponding trait level is here, but someone who is obtaining a score of 40, suppose, is having a corresponding trait level here. So you can directly compare, that's how you can directly compare the raw scores obtained by individuals and plot it against the theta level to understand the location of each of these items, each of these persons. Okay, so that's the advantage of estimating the person parameter. Okay, you can also get a person item map in item response theory using this RSM, RSM model, where this is the entire continuum, and it shows you the distribution of the person location as well as the item location. So ideally, it should be equally distributed across the entire continuum. Okay, the distribution of items and the distribution of persons should be more or less equal across the entire continuum. So that also gives you a measure of how your test is actually behaving, whether it is able to measure the entire range of the trait or not, whatever trait you are measuring, whether it is able to measure the entire trait or not. Okay, and since it is mathematically derived, it is a much more useful measure. So you can compare it across different samples, across, it's absolutely fantastic actually. So you can get the item statistics, which again gives you different measures of how each of these items are, functioning. As I was mentioning that in classical test theory approach, you can get only the very specific parameters like the difficulty index, discrimination index, like that, but not more than that. But in item response theory, you can get lot more actually. So you can get the outfit statistics, infit statistics. Okay, and looking at this will actually help you to a very, very large extent in refining the items which you are constructing and trying to validate. And once you use this type of measures to validate the items, it is hugely acceptable. You do not have to go for further, much more complicated measures. This alone will actually serve the validation process. So the last model that we have, the nominal response model, this is also the most, what should I say, the least understood, IRT model for polytomous responses. This is, mostly applicable for items where, for example, which are nominal in nature. For example, an item for assessing panic attack can be like, you are most likely to experience a panic attack when option A, you are with your family. Option B, you are in school. Option C, you are alone on the street. Option D, you are sleeping at home. And option E, after a fight with your parents and friends. Unlike the other different, rating scale categories, which are ordered in nature, where you have a, hierarchy, here we do not have any hierarchy, right? There is no ordered difference that you can see here. These are all nominal. These are all separate. So you cannot compare each of these options on a ordered scale. And that is why in such cases, for this type of items, the other IRT models are not applicable. Okay, here you have to use the nominal response model. Okay, so in nominal response model here also, a particular data set of the R has been used for the demonstration. And here, instead of the item difficulty and discrimination that we get for the other models, we get certain specific the type of estimates, which are the slope parameters and the intercept parameters. The A, which you can see here, A1, A2, A3, A4, these are the slope parameters that you get. And the C1, C2, C3, C4, these are the intercept parameters that you get for each of the items. Okay, and you compare the differences among these different slope parameters in order to understand which of a particular response category will be is more likely to be endorsed by individuals in comparison to another response category. All right, so you get this type of curves, which are a little different from the previous curves which we have seen, and you have to interpret it accordingly on the basis of the likelihood of getting endorsed by an individual. Okay, so which model to choose and when? Well, partial credit model is the simplest type of model, which considers only the item difficulty parameter, and if the rating scale has its own structure, okay, different structure for each of the items, then you go for PCM. Rating scale model, you can choose if all the items have a similar structure. There you go for rating scale model. GPCM and GRM, you can choose for all types of rating scales that you have, all the questionnaires that we have. If you want to get both the item location as well as the discrimination indices. And nominal response model, you choose if you have nominal response categories. So this is an example where you use a rating scale and a partial credit model. So if the first one that you can see here, this is a scale where you see all the items have a similar response category. So here, all of them, they have a 5-point rating scale, 1 indicating strongly disagree and 5 indicating strongly agree. All the items have the same structure. So here, rating scale model can be very easily applied. But in the second one, you see the first item being able to concentrate on what you are doing. The options are better than usual, same as usual, less than usual, much less than usual. Second item is lost much sleep over worry. The options actually change. Not at all, no more than usual, rather more than usual, much more than usual. Okay. Third one, again, the response categories change. So it has its own, different type of rating scale structure. The response categories keep on changing for each of the items. In these types of scales, the partial credit model is more applicable. All right. So I'll stop here. Thank you for your patient listening. If you have any specific question, please go ahead. Thank you. Ruchita, over to you.
Thank you so much, ma'am. If anyone have any question, you can please ask ma'am. Okay, so I would now like to call sir and say a few words.
Thank you, Dr. Shomana Datta. It is my honor to thank you again because you were the student of Psychology Research Unit. Once upon a time, you did extensive research on item response theory. Your thesis is also based upon the item response theory. And today, you have nicely covered the limitations of the classical test theory model and how we can overcome the limitations of classical test theory by using the item response theory. To item response theory, we can free from the sample distribution. We can, the second part, that is, we can control the redundancy and we can get the maximum test information. So I hope that is our students who have joined here, they will follow our YouTube video. And after that, if they have any question, they will write to us and we will send that question to you. So thank you, Dr. Datta, for your valuable time you have spent for us, because it's a long chapter. I think at least 5 days are required to learn the item response theory. So 1 or 2 hours is not sufficient, because all the trainees have the very clear-cut idea about the CTT, but item response theory and this mathematical model, theta model, Rasch model, all those things, and GRM. So this is totally unknown to most of the people. I hope that is in near future, we will be able to arrange some more program on this issue.
Right.
Datta.
Thank you so much, sir. Thank you. Thank you all the participants for your patient listening. I hope at least from this workshop, you got a overview of the item response theory. And of course, it is not something that you can learn in 2 hours, as sir mentioned. It requires a lot of time to understand, to get into the vibe of it, and then understand and apply it in your own work. I also required a lot of time. So my best wishes to all of you. I'll definitely suggest some of the books. I'll give the suggestions to Ruchita, and maybe she will be able to distribute it among all of you. So thank you again. Thank you very much, sir, for inviting me, and thank you again.
Okay, students, do you have any question? Hello? Or no question? Only thing that is your impression about Madam's class. Ayushi? Ayushi is very sincere student. Ayushi attended several internship program in ISI. Ayushi, are you here? Ayushi has strong interest in item analysis. Possibly she has some network problem. Okay. Okay, thank you. Thank you, Shona. Thank you.
Thank you, sir.
Okay, so tomorrow we'll again begin the workshop at 11 a.m. Okay, and continue till 4 p.m. as per the schedule given. Thank you all for attending.